We'll start in 1 minute. Today we're going to cover the first part of the Test 3 review, and then tomorrow we'll cover the rest of it. Test 3 is on Friday, and more practice if you want more practice for Test 3. On YouTube there are 2 playlists. One is called Math 1108 Test 3 Review Sheet Videos, and the other playlist, Math 1108 Chapter 7 and Chapter 8 material, Test 3 material. And the test will be Zoom proctored. Let's get started with the review. From section 7.1 and 7.4. In 7.1, that was the section that discussed restricted values. Those are the x values that make the denominator 0. And they're restricted because division by 0 is undefined. And then in section 7.4, that is where we learned how to solve equations with rational expressions. So first we'll identify the restricted values. The restricted values are the x values that make the denominator 0. If you look at this denominator x minus 2, the restricted value in that denominator is 2. So we say x cannot be 2. This denominator is x plus 1. So the x value that makes that denominator 0 is negative 1. So the second restricted value is negative 1. And this denominator, x squared minus x minus 2, is just the product of x plus 1 times x minus 2. So we don't get any more restricted values than the 2 that we already have. The least common denominator is just the product of x plus 1 times x minus 2. When you multiply them, you get the other denominator. So that's the least common denominator, x plus 1 times x minus 2. And in expanded form, it's x squared minus x minus 2. Okay, so we want to know what the least common denominator is so that we can clear the denominators, which is to say that we're going to reduce every denominator to a factor of 1. So we'll multiply every term on both sides by the least common denominator. And the term on the left, the rational expression on the left, we'll multiply that by x squared minus x minus 2 over 1 times x minus 1 over x squared minus x minus 2. And then multiply the next term, x plus 2 over x plus 1. This time I'll use the factored form of the least common denominator. So it's x plus 1 times x minus 2 over 1 times x plus 2 over x plus 1. And then also on the right-hand side, I'll use the factored form of the least common denominator. X plus 1 times x minus 2 over 1 multiplied by x minus 1 over x minus 2. Okay, so we're going to clear the denominators now. In this first product, the trinomial factor x squared minus x minus 2 divided by the same trinomial factor equals 1. So these factors cancel each other out. And we're left with just x minus 1. In the next product, the denominators are cleared. The denominator is cleared because if we divide the factor x plus 1 by the same factor x plus 1, we're just left with x minus 2 times x plus 2. And then on the right-hand side, we'll clear the denominator also. In the numerator, the factor x minus 2 divided by the denominator x minus 2, we're just left with x plus 1 times x minus 1. Now we just do a little bit of algebra and arithmetic. On the left-hand side, we have x minus 1. And then when we multiply x minus 2 times x plus 2, we get x to the second plus 2x, and then minus 2x and minus 4. On the right-hand side, x plus 1 times x minus 1 is x to the second minus x plus x minus 1. And we'll combine like terms. Notice the 2x minus 2x, those combine to make 0, so those cancel each other out. And on the right-hand side, the minus x plus x, those also add up to 0, so those cancel each other out. Notice we have another cancellation. Both sides of the equation have x squared, so when we subtract x squared from both sides, those are eliminated. So let's write down what we have left. On the left-hand side, we have x minus 1 minus 4, which is x minus 5. And on the right-hand side, we just have minus 1 or negative 1. And now all we have to do is add 5 to both sides. And negative 1 plus 5 is 4. 4 is not a restricted value. And so 4 is the solution. If you want to double check, you can replace every x in the original equation with 4 and verify that you'll get a true result if you do so. But we won't do that here. We'll just move on to the next example. Okay, so the next example, same process, just a different equation with rational expressions. First, find the restricted values. One of the denominators is y minus 7. So the restricted value we get from that denominator is 7. So y is not 7. This denominator on the left, y minus 2, that restricted value is 2. And things work out nicely in this course. This denominator, y squared minus 9y plus 14, that's just what you get when you multiply y minus 2 times y minus 7. So we don't get any more restricted values than the ones that we already have. And the least common multiple of the denominators, or the least common denominator, is just y minus 2 times y minus 7. And then in expanded form, it's y squared minus 9y plus 14 in expanded form. So we multiply every term on both sides by the least common denominator. You can either use the factored form or the expanded form. And then we choose which one just based upon what we're multiplying it by. So I'll multiply y minus 4 over y minus 2 by the factored form of the least common denominator. So y minus 2 times y minus 7 over 1 times y minus 4 over y minus 2. Well, I started a little too high, so I'm going to have to dodge the least common denominator, but we'll manage, maybe. So minus, and then we multiply this term by the least common denominator in expanded form. So that's y squared minus 9y plus 14 over 1 times 3 over y squared minus 9y plus 14. And then on the right-hand side, we'll use the factored form of the least common denominator, y minus 2 times y minus 7 over 1 times y minus 8 over y minus 7. Okay, it looks worse before it gets better, but we'll proceed. In this first product, y minus 2 from the numerator cancels with this y minus 2 from the denominator. So we cleared the denominators here, and we're just left with y minus 7 times y minus 4. And then minus, in this next product, the trinomial factor divided by the same trinomial factor, those cancel each other out. So we're just left with minus 3. And then on the right-hand side, the y minus 7 factor from the numerator cancels with the y minus 7 factor in the denominator, and we're just left with y minus 2 times y minus 8. Okay, then we do algebra and arithmetic. So let's multiply y minus 7 times y minus 4. We get y to the second minus 4y minus 7y, and then negative 7 times negative 4 is positive 28. So it's plus 28 minus 3. And on the right-hand side, y minus 2 times y minus 8, y to the second minus 8y minus 2y plus 16. Notice that both sides of the equation have y to the second. So those, when we subtract y to the second from both sides, those are eliminated. And let's just combine like terms on each side. On the left-hand side, minus 4y minus 7y is a total of negative 11y. And then plus 28 minus 3, that simplifies to plus 25. And then on the right-hand side, minus 8y minus 2y simplifies to negative 10y, and then plus 16. So we can proceed in a couple of ways, but what I'm going to do, I'm going to add 11y to both sides, and we'll get 25 equals y plus 16, because negative 10y plus 11y is just 1y. And then we can subtract 16 from both sides, and we get the solution, y equals 9. So y equals 9 is not a restricted value, and if you want, you can verify you can check that 9 really is the solution. Okay, we'll move on then to section 7.5, where we have word problems that involve rational equations. Okay, the first one, solve the word problems with rational equations. This one says Evan takes 3 hours to clean the barn stalls by himself, and Doug takes 4 hours to do the job by himself. How long will it take them to clean the stalls if they work together? Well, this problem describes completing a job, one job. So equations will have the form rate times time equals 1. For Evan works for 3 hours to clean the barn stalls by himself. So Evan works at his rate R sub E for Evan's rate multiplied by 3 hours equals the completion of one job. So rate times time equals 1 for Evan. For Doug, we're told that Doug takes 4 hours to do the same job by himself. So Doug's rate, R sub D, times 4 hours equals 1. And we're supposed to find how long it takes them when they work together. So when they work together, Evan works at his rate, R sub E. We add that to Doug's rate. And we want to find how much time it takes them when they work together. So here's where we assign the variable. Whenever we're asked to find a particular quantity in algebra, we pick a letter or a variable to represent that quantity. So I'm just using capital T for the time it takes them when they work together. So we have 3 equations, each having the form rate times time equals 1. So what we want is an equation whose only variable is t. So our intermediate step is to solve each of the equations for the rate. Evan's rate is 1/3, which means he can clean 1/3 of the stalls per hour. That's his hourly rate. Doug's hourly rate is 1/4 of the job per hour. Then when they work together, Evan's rate plus Doug's rate is 1/T. Okay, so now we can write an equation whose only variable is t. So replace Evan's rate with 1/3, since that's what Evan's rate is. Replace Doug's rate with 1/4, and 1/3 plus 1/4 equals 1/T. Okay, the standard way to solve this equation for t, since t is in the denominator, is to multiply every term on both sides by the least common denominator. The least common multiple of the denominators 3, 4, and t is just 12t. And you can think of that as 12t over 1 if it helps. Okay, so we'll multiply every term on both sides by 12t over 1. 12t over 1 times 1/3 plus 12t over 1 times 1/4 equals 12t over 1 times 1/T. And then we just do the arithmetic. 12t divided by 3 is 4t. 12t divided by 4 is 3t. On the right-hand side, 12t divided by t is 12. And then 4t plus 3t is 7t. So 7t equals 12. And then divide both sides by 7. T equals 12/7 hours. So it's not quite 2 hours, but 1 hour, 1 hour and 5/7 of an hour. But this is an okay answer. And then probably should write the units. 12/7 hours is how long it takes Doug and Evan to clean the stalls when they work together. Okay, the next problem, this one says it takes Greg 1 hour longer to walk 12 miles than it takes Chris to walk 12 miles. Greg's walking rate is 2 miles per hour slower than Chris's walking rate. Find their walking rates. Okay, so what kind of word problem is this? Well, the clues are in the problem itself. A distance of 12 miles is described. Greg walks a distance of 12 miles, and Chris also walks a distance of 12 miles. A certain amount of time is mentioned. Regarding time, Greg takes 1 hour longer than Chris to walk 12 miles. And rates are mentioned. Greg's walking rate is 2 miles per hour slower than Chris's walking rate. So the equations we need for this problem are rate times time equals distance. But let's assign the variables first, and there are options that are equivalent when assigning variables. So for Greg, for Greg's rate, I'll just pick X measured in miles per hour. And then for Chris's rate, well, Chris's rate, since we've already picked X to represent Greg's rate, then Chris's rate will have to reflect the information given. In the second sentence, we're told that Greg's walking rate is slower than Chris's by 2 miles per hour. So Chris's rate or walking rate is X plus 2 miles per hour. So you can verify X is 2 smaller than X plus 2. Okay, the amounts of time each walks 12 miles is different, so we'll take that into account a little bit later. But for now, let's go ahead and write the rate times time equals distance equations for Greg and Chris. For Greg, X is his rate. Let's use T sub G for the amount of time it takes Greg to walk a distance of 12 miles. We don't know specifically how much time that is right now. And Chris, his rate is X plus 2 miles per hour. And let's use T sub K to represent the amount of time it takes Chris to walk a distance of 12 miles. And then in the problem, we're told how the amount of time it takes Greg to walk 12 miles relates to how much time it takes Chris to walk 12 miles. So we're told in the very first sentence, it takes Greg 1 hour longer to walk 12 miles than it takes Chris. So the amount of time it takes Greg to walk 12 miles is greater than the amount of time it takes Chris to walk 12 miles. It's greater by 2. Okay, so we can convert this into an equation in one of 3 ways, but the way that I prefer is just to subtract the smaller number from the larger number. So in other words, the larger number, Greg's time, minus the smaller number, Chris's time, is equal to 2. We're told that they differ by 2, so this has to be the equation. Okay, so this sort of tells us what we need to do. We need an equation whose only variable is X. So the intermediate work, we're going to solve each of these 2 equations for the time. Greg's time is equal to his distance divided by his rate, 12 divided by X. Chris's time is his distance divided by his rate. And then we substitute each of those into this equation. So Greg's time is his distance divided by his rate, 12 over X. And we subtract Chris's time, which is his distance divided by his rate, X plus 2. And the difference is 2 hours. Greg's time minus Chris's time is 2 hours. Okay, so finally we have an equation whose only variable is X. X appears in each of 2 denominators. So the method is multiply both sides of the equation, every term on both sides, by the least common denominator. The least common denominator is just X times X plus 2. Think of that as X times X plus 2 over 1, if you like. So we'll multiply every term on both sides by this least common denominator. We'll do a little bit of shortcutting When we multiply 12 over x times x plus 2 over 1, the x's cancel, and we'll just be left with 12 times x plus 2. And then minus, when we multiply 12 over x plus 2 by x times x plus 2, the x plus 2 factors cancel, and we'll just be left with minus 12x. And then on the right-hand side, we don't get a cancellation. Another way to write the least common denominator is an expanded form. It's x squared plus 2x. So let's just multiply 2 times the entire quantity x squared plus 2x and write it as 2x squared plus 4x. Okay, so now we just solve this equation. Apply the distributive property. We get 12x plus 24 minus 12x equals 2x squared plus 4x. Notice on the left-hand side, the 12x minus 12x, those cancel. And then we'll just subtract 24 from both sides, so we get 2x squared plus 4x minus 24 equals 0. And then, just to make things simpler, let's just divide every term on both sides by 2. So we get x squared plus 2x minus 12 equals 0. And then we can solve this by factoring. One factor is x plus 6, and the other factor is, so something went wrong. So I must have made a mistake somewhere. So for now, let's just move on, and I'll try to come back to that later. I'll have to rework it. But yeah, that's not working out. So I apologize. We'll come back to that later if we have time. Let's look at section 7.6, solve rational inequalities. So this is all set up the way that we want. One side is 0, and we can identify the endpoints. The endpoints are the x values that make the numerator 0 and the denominator 0. So the x value that makes the numerator 0 is positive 2, and the x value that makes the denominator 0 is negative 3. So we divide the number line into 3 separate intervals by plotting those endpoints, negative 3 and 2. Those divide the number line into 3 separate intervals. And then we pick a test point from each interval. In the first interval, we can pick x to be negative 4. And then in the numerator, replace x with negative 4. Negative 4 minus 2 is negative 6. In the denominator, negative 4 plus 3 is negative 1. And negative 6 divided by negative 1 is positive 6. And 6 greater than 0 is true. So yes, all of the numbers in the interval from negative infinity to negative 3 are solutions. In the middle interval, we can pick x to be 0 and then replace every x with 0. In the numerator, we get negative 2. 0 minus 2 is negative 2. in the denominator, 0 plus 3 is 3, and negative 2/3 greater than 0 is false. So none of the numbers between negative 3 and 2 are solutions. In the third interval, we can pick x to be 3. And in the numerator, 3 minus 2 is 1. In the denominator, 3 plus 3 is 6. The inequality is greater than 0. 1/6 greater than 0 is true. So all of the numbers from 2 to infinity are solutions. And since the inequality is greater than, the endpoint from the numerator is excluded. So we put a parenthesis at 2. Endpoints that come from denominators are never part of the solution, no matter what. So we put a parenthesis at negative 3. Okay, the directions say write the solutions in algebraic and interval notation. I'll write the interval notation first. The left interval from negative infinity to negative 3, excluding 3, is written this way. This is the interval notation. And then we put the union symbol, and then this set of numbers from 2 to infinity, excluding 2, is parenthesis 2, comma, infinity. That's the interval notation. The algebraic notation, this set of numbers on the left, that's x is less than negative 3. And then we write the word or, and then x is greater than 2. The next example is similar to the one that we just did. So we'll bypass this one, but I will mention about the endpoints. The endpoint 5 that comes from the denominator is excluded. So there's a parenthesis next to 5 in the interval notation. But the endpoint that comes from the numerator is included. The endpoint is negative 1. And negative 1, replace every x with negative 1. The inequality 0 less than or equal to 0 is true. It's the or equal to 0 that makes it true. So you would use a bracket next to the negative 1 in the interval notation. Okay, let's do the next one though. This one's a little more involved. So let's go ahead and factor the denominator. The numerator is just x minus 5. The denominator in factored form is x minus 3 times x plus 2, greater than or equal to 0. So the endpoint that comes from the numerator is 5. From the denominator, 3 is one of the endpoints because of the factor x minus 3. And then the other endpoint from the denominator is negative 2. Okay, so we divide the number line into 4 separate intervals this time. Negative 2 is to the left of 3, which is to the left of 5. So we have 4 intervals to test. Okay, so on the left, in the interval on the left, we'll pick x to be negative 3. And I'll just use the factored form of the denominator. When x is negative 3 in the numerator, negative 3 minus 5 is negative 8. In the denominator, this factor, negative 3 minus 3 is negative 6. And the other one, negative 3 plus 2 is negative 1. And this number, a negative divided by a negative times a negative is negative. This is negative 4/3 greater than or equal to 0. That's false. So none of the numbers from negative infinity to negative 2 are solutions. In the second interval, we can pick x to be 0. This time, using the original rational expression might be easier. Replace every x with 0, you get negative 5 divided by negative 6, which is positive 5/6. And the inequality greater than 0 is true this time. So yes, all of the numbers between negative 2 and 3 are solutions. In the third interval, we can pick x to be 4. And then I'll use the factored form again. 4 minus 5 in the numerator is -1. In the denominator, 4 minus 3 is 1, and then 4 plus 2 is 6. So this number is negative, -1/6. The inequality greater than or equal to 0 makes it false. That's a false statement. So none of the numbers from 3 to 5 are solutions. And then finally, in the fourth interval, we can pick x to be 6. And then I'll use the factored form again. In the numerator, 6 minus 5 is 1. In the denominator, 6 minus 3 is 3. And 6 plus 2 is 8. This is a positive number. The inequality is greater than or equal to 0, and that's true. So yes, all of the numbers from 5 to infinity are solutions. And we include the endpoint that comes from the numerator. We include 5 because 5 makes the left-hand side 0, and 0 greater than or equal to 0 is true. So we put a bracket at 5 and shade to the right graphically. And then we exclude the endpoints that come from the denominator in every case. So we use parentheses at 2 and 3 and shade everything in between. Okay, the interval notation for this set of numbers from -2 to 3, excluding -2 and 3, is parenthesis -2, 3, and then union bracket 5, comma, infinity. That is the interval notation. And then the algebraic notation, this set of numbers from -2 to 3, excluding the endpoints, we write -2 less than x, which is less than 3. And then or, when x is in this set from 5 to infinity, including 5, we write x is greater than or equal to 5. Okay, we'll move on then to Chapter 8 material. Simplifying roots and radicals. So simplify the square root of 81 x to the 14th. Both 81 and x to the 14th are perfect squares. The square root of 81 is 9, and the square root of x to the 14th is x to the 7th, because the exponent 14 divided by the index 2 is 7. Square roots have indexes that are equal to 2. So that one is pretty easy. The next example, the cubed root of -125 is just -5. The fourth root of 64 doesn't simplify to an integer because 64 it's not a perfect fourth power. The largest factor of 16 that is, sorry, the largest factor of 64 that is a perfect fourth power is 16, and 16 times 4 is 64. So we can rewrite the fourth root of 64 as the fourth root of 16 times the fourth root of 4. And then in the next step, -5 plus, the fourth root of 16 is 2, because 2 to the fourth is 16. And so -5 plus 2 times the fourth root, 4. That's the final answer on that one. Okay, the next one, the fourth root of 16 simplifies to 2. And minus the square root of 16, the square root of 16 is 4, so 2 minus 4, and that simplifies to -2. Okay, in the next example, the square root of 121x to the 10th, y to the 22nd. This simplifies so that in the end we don't have any square roots left, because 121 is a perfect square. X to the 10th and y to the 22nd are both perfect squares because the exponents are multiples of 2. The square root of 121 is 11. The square root of x to the 10th is x to the 5th. And the square root of y to the 22nd is y to the 11th. So that simplifies nicely. Okay, the next one, there's a little more work involved. Simplify the square root of 98 n to the 33rd. The largest factor of 98 that's a perfect square is 49. 49 times 2 is 98. The largest factor of n to the 33rd that's a perfect square is n to the 32nd, because the exponent 32 is a multiple of 2. So we can rewrite this as the square root of 49 n to the 32nd times the square root of 2n. And then we simplify the square root of the perfect square factors. Square root of 49 is 7. The square root of n to the 32nd is n to the 16th, multiplied by the square root of 2n. That's the simplified result. Okay, in the next example, we have a square root of a quotient. So notice that the quotient can be written in lower terms, which is to our benefit. 72 over 98 can be reduced to 36 over 49. So we can write this as the square root of 36 times x to the 21st over 49 times y to the 14th. Then we can use the quotient property of radicals and write it as the square root of 36 times x to the 21st in the numerator, divided by the square root of 49 y to the 14th in the denominator. 36 is a perfect square, and the largest factor of x to the 21st that is a perfect square is x to the 20th. And in the denominator, 49 is a perfect square, and so is y to the 14th. So in the numerator, we can write it as the square root of 36 x to the 20th times the square root of x. And we can go ahead and simplify the denominator. That simplifies to 7 times y to the 7th. And then finally, in the numerator, the square root of 36 is 6. The square root of x to the 20th is x to the 10th. And so 6 times x to the 10th times the square root of x is in the numerator. And then the denominator is already simplified, 7y to the 7th. Okay, in the last part, the cubed root of 250 m to the 30th divided by 16 n to the 24th. Well, we can also write this quotient in lower terms. 250 over 16 reduces to 125 over 8. So we get the cube root of 125 m to the 30th over 8 n to the 24th. And then you can write it as a quotient of cube roots, the cube root of 125 m to the 30th in the numerator. And in the denominator, the cubed root of 8 n to the 24th. And all of the factors are perfect cubes. The cubed root of 125 is 5 because 5 cubed is 125. M to the 30th is a perfect cube because the exponent 30 is a multiple of 3. So the cubed root of m to the 30th is m to the 10th because 30 divided by 3 is 10. And in the denominator, the cubed root of 8 is 2 because 2 to the 3rd is 8. And the cubed root of n to the 24th is n to the 8th because 24 divided by 3 is 8. Okay, we'll do a few more simplifying radicals. So this one, the square root of 75x to the 23rd, the largest factor of 75, that's a perfect square, is 25. 25 times 3 is 75. And the largest factor of x to the 23rd, that's a perfect square, is x to the 22nd. So we can rewrite this as the square root of 25x to the 22nd multiplied by the square root of the remaining factors, 3 times x, square root of 3x. And then simplify the square root of 25 to 5, simplify the square root of x to the 22nd to x to the 11th, and then multiply 5 times x to the 11th by the square root of 3x. Okay, in the next example, the fifth root of negative 64x to the 28th. Well, a factor of negative 64 that's a perfect fifth power is negative 32, because negative 2 to the fifth is negative 32. And then the largest factor of x to the 28th that is a perfect fifth power is x to the 25th, because 25 is a multiple of 5. So we'll rewrite this as the cubed root of negative 32x to the 25th times the, I think I said that wrong, the fifth root of negative 32x to the 25th times the fifth root of the remaining factors, 2x to the third. And then we look at the other radical, the fifth root of 32. 32 is a perfect fifth power, and the largest factor of y to the 18th, that's a perfect fifth power, is y to the 15th. So we can rewrite this as the fifth root of 32 y to the 15th multiplied by the fifth root of the remaining factors, y to the third. And then in the next step, we can write this simplified form. The fifth root of negative 32 is negative 2, and the fifth root of x to the 25th is x to the 5th, because 25 divided by 5 is 5. So negative 2x to the 5th times the fifth root of 2x to the 3rd, and then plus the fifth root of 32 is 2. The fifth root of y to the 15th is y to the 3rd, because the exponent 15 divided by the index 5 is 3. And so plus 2x to the 3rd times the fifth root of y to the 3rd. Okay, in the next example, the fourth root of 48x to the 10th minus the square root of 72y to the 20th. The largest factor of 48, that's a perfect fourth power, is 16. And the largest factor of x to the 10th, that's a perfect fourth power, is x to the 8th. So we'll rewrite this as the fourth root of 16x to the 8th times the fourth root of 3x to the 2nd. And then in the next one, the largest factor of 72, that's a perfect square, this is a square root, is 36. 36 times 2 is 72. And y to the 20th is a perfect square because the exponent is a multiple of 2. So we can write this as minus the square root of 36y to the 20th times the square root of 2. And then in the next step, we can write the simplified answer. The fourth root of 16 is 2. The fourth root of x to the 8th is x to the 2nd. 8 divided by 4 is 2. And then times the fourth root of 3x to the 2nd. And then minus the square root of 36 is 6. The square root of y to the 20th is y to the 10th. So minus 6y to the 10th times the square root of 2. Okay, in the next example, even though the 45 over 25 can be written in lower terms, it's to our advantage to not write that in lowest terms this time. That might seem strange, that sometimes we do and sometimes we don't. If we did, we would just have to fix it, because in general, we don't want a radical in the denominator. Notice that this denominator simplifies to 5y to the 13th with no radical. If I had reduced the fraction to lower terms, then we would have ended up with a radical in the denominator, and we would have to fix that later. You can do it that way, but it's more efficient to do it this way. And then we work on the numerator. The largest factor of 45, that's a perfect square, is 9. The largest factor of x to the 27th, that's a perfect square, is x to the 26th. So we're about out of time. This will be the last one we do. So the square root of 9x to the 26th times the square root of 5x. And then the last step, the square root of 9 is 3. The square root of x to the 26th is x to the 13th. So 3x to the 13th times the square root of 5x, all divided by 5 times y to the 13th. Okay, we're out of time. I'll email you with a correction on that word problem that I made a mistake on, and just to clear that up. And then tomorrow we'll continue the test 3 review. Stupid. Okay, it's time to start. We'll continue the review from where we left off last time. Okay, on this one, simplify the fourth root of 48x to the 10th minus the square root of 72y to the 20th. The largest factor of 48 that's a perfect fourth power is 16. 16 is 2 to the fourth. The largest factor of x to the 10th that's a perfect fourth power is x to the 8th, because 8 is a multiple of 4. This one's a square root. The largest factor of 72 that's a perfect square is 36. 36 times 2 is 72. Y to the 20th is a perfect square because the exponent is a multiple of 2. So we'll rewrite this as the fourth root of 16 x to the 8th times the fourth root of the remaining factors, 3x to the 2nd. And then over here, write this as the square root of 36y to the 20th times the square root of 2. And then in the next step, we can write the completely simplified expression. The fourth root of 16 is 2. The fourth root of x to the 8th is x to the 2nd, because 8 divided by 4 is 2. So 2x to the 2nd times the fourth root of 3x to the 2nd. And then minus the square root of 36 is 6. The square root of y to the 20th is y to the 10th. So it's minus 6y to the 10th times the square root of 2. Okay, in this next example, we have a square root. Notice that in the denominator, we already have a perfect square, 25y to the 26th. So even though we could write the quotient in lower terms, it's to our advantage in this case to not write it in lower terms, because we would just have to undo that later. So we'll just rewrite this as the square root of 45x to the 27th in the numerator, and then divided by the square root of 25y to the 26th in the denominator. And in the next step, the square root of 25y to the 26th simplifies to 5y to the 13th with no square root, which is what we want. We don't want square roots in the denominator. And then in the numerator, we have some work to do. The square root of 45, the largest factor of 45 that's a perfect square is 9. 9 times 5 is 45. The largest factor of x to the 27th, that's a perfect square, is x to the 26th. So we'll rewrite the numerator as the square root of 9x to the 26th multiplied by the square root of the remaining factors, 5x. And then finally, the square root of 9x to the 26th is 3x to the 13th. So in the numerator, we have 3 times x to the 13th times the square root of 5x, and then divided by 5y to the 13th. Okay, in the next example, the cubed root of the quotient 250 m to the 21st over 27 n to the 30th. We'll rewrite this as a quotient of cubed roots. So in the numerator, we have the cubed root of 250 m to the 21st. And in the denominator, the cubed root of 27 n to the 90th. So it seems like my writing is getting worse. But oh well. The largest factor of 250 that is a perfect cube is 125. 125 times 2 is 250. M to the 21st is a perfect cube because the exponent 21 is a multiple of 3. And then in the denominator, 27 is a perfect cube, and so is n to the 90th because 90 is a multiple of 3. So we'll rewrite this as in the numerator, the cubed root of 125 times m to the 21st multiplied by the cubed root of 2. And in the denominator, we can go ahead and simplify this. The cubed root of 27 is 3. The cubed root of n to the 30th is, the cubed root of n to the 90th is n to the 30th, because 90 divided by 3 is 30. And then finally, in the last step, the cubed root of 125 is 5. Cubed root of m to the 21st is m to the 7th. 21 divided by 3 is 7. So the numerator is 5 times m to the 7th times the cubed root of 2. And then in the denominator, we just have 3n to the 30th. Okay, the next page, we'll look at some rational exponents, simplifying rational terms with rational exponents, or exponents that have fractions in them. Okay, notice this doesn't say to convert to radical form, it just says to simplify. So the denominator of the exponent is 2, so that suggests a square root. So we can think of this as 81 to the 1/2 to the 3rd, because the exponent 3 times the exponent 1/2 is 3/2. And then on the inside of the parentheses, 81 to the 1/2, that's just the square root of 81, so it's 8 to the 3rd. And then 8 to the 3rd is 8 times 8 is 64, and 64 times 8 is 512. With your high-powered calculator, that shouldn't be too hard. The next one, negative 27 to the 2/3. The denominator of the exponent is 3, so that implies that we want the cubed root of negative 27. And then afterwards, we'll raise it to the 2nd power. We're just applying properties of exponents. The exponent 2 times the exponent 1/3 is the exponent 2/3. But then on the inside, the number negative 27 to the 1/3, that's just the number negative 3. And then negative 3 to the 2nd is positive 9. Okay, the next example, we have 5 to the 3/2 times 5 to the 5/2. We're multiplying and the bases are the same, so we apply the property that says that we write the base number but then add the exponents. So 5 to the 3/2 plus 5/2, and then 3/2 plus 5/2 is 8/2, but 8/2 is 4, so we get 5 to the 4th. And then we can simplify 5 to the 4th. That just turns out to be 625. 5 times 5 times 5 times 5 is 625. Okay, the next one. Well, in the numerator, 64 to the 1/2, that just means the square root of 64, which is 8. In the denominator, we have 25 to the 3/2. So the denominator of the exponent is 2. So we can rewrite this as 25 to the 1/2 raised to the power 3. So the numerator is already simplified. In the denominator, 25 to the 1/2, that's just the square root of 25. So we get 5 to the 3rd. And we can evaluate 5 to the 3rd. So we get 8 over 125 is the simplified answer to that one. Okay, these, well, just always in general, just read the directions to know what you're supposed to do. Convert from radical form to rational exponent form. So the fifth root of 7x squared y to the fourth, well, we start by writing 7x to the second y to the fourth to the outer exponent 1/5. And then we can apply one of the properties of exponents and write it as 7 to the 1/5 times x to the 2/5, because 1/5 times 2 is 2/5, times y to the 4/5, because 1/5 times 4 is 4/5. So it was assumed, which is a correct assumption, that 7 can be written as 7 to the first. So when we multiply exponents, we multiply 1/5 times 1 to get 7 to the 1/5. Okay, and the next one, convert this radical to rational exponent form. This is the cubed root. The index is 3. So we're going to raise the quantity 8x to the second y to the 1/3. And then applying a property of exponents, we can write this as 8 to the 1/3 times x to the 1/3 times 2 is x to the 2/3 times y to the 1/3 times 1 is y to the 1/3. And we can simplify further because the cubed root of 8 simplifies to 2. Or in rational exponent form, 8 to the 1/3 simplifies to 2. So our final answer is 2 times x to the 2/3 times y to the 1/3. Okay, we have 3 more problems to look at in section 8.3, or from related to section 8.3. So some of these are a little bit extracurricular, but this will help you be better prepared for the final if you can do these other examples. So on this one, simplify these expressions. 8x to the 6th, y to the 6/5. This is all raised to the 2/3 power. So when we apply the property of exponents, we get 8 to the 2/3 times y to the, the next one is x to the 6 times 2/3, we'll simplify that in a second, times y to the 6/5 times 2/3. Okay, so for 8 to the 2/3, well, we know that 8 is a perfect cube and the denominator of the exponent is 3. So let's think of that as 8 to the 1/3 to the second, because 2 times 1/3 is 2/3. And then we can simplify this, x to the 6 times 2/3, that's x to the 12 divided by 3, or x to the 4th. And then y to the 6/5 times 2/3, well, that's y to the 12/15, but 12/15 simplifies to 4/5. So we get y to the 4/5. Okay, just a couple more steps. 8 to the 1/3, the cube root of 8 is 2. Maybe we'll just do it all at once. This is going to simplify to 2, and then 2 to the second is 4. So our final answer is 4x to the 4th times y to the 4/5. Okay, on the next one, well, inside the parentheses, in the numerator, we have 9m to the negative 2/3 times 4n to the 1/3. And in the denominator, we have 16m to the 5/6 times 25 times n to the negative 1/6. So let's just go ahead and apply the outer exponent. So in the numerator, we get 9 to the 3 halves times m to the negative 2/3 times 3 halves times 4 to the 3 halves times n to the 1/3 times 3 halves. And then in the denominator, 16 to the 3 halves times m to the 5/6 times 3 halves times n to the negative 1/6 times 3 halves. And then we'll just evaluate all of those, simplify those. So think about 9 to the 3 halves. The denominator of the exponent is 2, so that involves a square root of 9. Square root of 9 is 3, and then we raise 3 to the exponent, the numerator of the exponent, 3 to the 3rd. So in other words, 9 to the 3 halves simplifies to 27. M to the negative 2/3 times 3 halves is m to the negative 1. 4 to the 3 halves, well, the denominator of the exponent is 2, so that means find the square root of 4, which is 2, and then raise 2 to the 3rd power. So you can verify that 4 to the 3 halves simplifies to 8, and then n to the 1/3 times 3 halves is n to the 1/2. So things are looking a little better. In the denominator, 16 to the 3 halves, the denominator is 2, so that means find the square root of 16, which is 4, and then raise 4 to the 3rd power. 4 to the 3rd power is 64. And then m to the 5/6 times 3 halves. Well, this is just going to simplify to 15 over m to the 15 over 12, but 15 over 12 reduces to 5/4. Yeah, so m to the 5/4. And then, darn, I forgot the 25. So I'll write this 25 to the 3 halves right here. But 25 to the 3 halves, the square root of 25 is 5, and then 5 to the 3rd is 125. And then n to the negative 1/6 times 3 halves is just n to the negative 1/4. Okay, so let's take it one step further. Notice the 8 divided by 64. This cancels and this becomes 8. So we can rewrite the numerator with a factor of 27 in it. And the variable n will be in the numerator. So n to the 1/2 divided by n to the negative 1/4. If we move the term to the numerator, it becomes n to the 1/2 times n to the positive 1/4. And so this will be n to the 1/2 plus 1/4. And then in the denominator, we have 8 times 125, but that's just 1,000. And then the variable m, that's the only thing we have left. In the numerator, we have m to the negative 1, and in the denominator, we have m to the 5/4. So in the denominator, m to the negative 1 in the numerator is equivalent to m to the positive 1 in the denominator, and m to the 1st times m to the 5/4 is m to the 9/4 because we add the exponents. And then this exponent This just simplifies to 3/4. So I'll go ahead and write the last form, 27n to the 3/4 all over 100 m to the 9/4. Okay, so let's go ahead and bypass this next example. We'll look at a few examples where we add and subtract and then multiply radical expressions. So here we're subtracting and adding, so we always want to simplify square roots or radicals first. So we can simplify each of those. And so when we simplify the square root of 50y to the 7th, we can rewrite that as the square root of 25y to the 6th times the square root of 2y, because 25y to the 6th times 2y is 50y to the 7th. And 25 and y to the 6th are perfect squares. And the next one, the largest factor of 98 that's a perfect square is 49. And the largest factor of y to the 7th that's a perfect square is y to the 6th. So we can write this as the square root of 49y to the 6th times the square root of 2y. And then plus, then the next one, the square root of 18y to the 7th. The largest factor of 18 that's a perfect square is 9. 9 times 2 is 18. And the largest factor of y to the 7th that's a perfect square is y to the 6th. So we get the square root of 9y to the 6th times the square root of 2y. Okay, we simplify the square roots of the perfect squares. So here we get 5y to the 3rd times the square root of 2y. And then minus 7y to the 3rd times the square root of 2y. And then plus 3y to the 3rd times the square root of 2y. And we can combine all three into a single term because the square roots are identical, the simplified square roots, and the variable parts on the outside are also the same. So 5 of those minus 7 of the same plus 3, all together we're just left with 1 times y to the 3rd times the square root of 2y. That's the simplified result. Okay, we'll skip this one. I want to make sure that we get a sample of all of the types of problems that we need to review for Friday's test. But I'll just mention when adding and subtracting radicals, simplify the radicals as much as possible first. And then if they are like radicals, then you can combine them by adding and subtracting. But if they are unlike radicals, you cannot combine them by adding and subtracting. Okay, in the next example, we're just multiplying two square roots. So the square root of 50x to the 15th times y to the 7th times the square root of 8x to the 5th y to the 13th. So what I recommend is if you're multiplying two radicals with the same index, like two square roots, write it as a single radical with the same index and multiply the arguments or the radicands. So 50 times 8 is 400. X to the 15th times x to the 5th is x to the 20th. And then y to the 7th times y to the 13th is y to the 20th. And it turns out in this case that each of those factors is a perfect square, so we can simplify without a square root in the end. The square root of 400 is 20. The square root of x to the 20th is x to the 10th. And the square root of y to the 20th is y to the 10th. Okay, in the next example, we're multiplying two expressions involving radicals. So we multiply these like we would just multiply binomials. So we have 5 times the square root of 5 times the square root of 5. This is 5 times the square root of 25. And then we have 5 times the square root of 5 times 4 times the square root of 3. 5 times 4 is 20, so it's plus 20, and then times the square root of 15, because the square root of 5 times the square root of 3 is the square root of 15. And then we're going to subtract the square root of 3 times the square root of 5, which is just minus the square root of 15. And finally, minus the square root of 3 times 4 times the square root of 3 is minus 4 times the square root of 9. Okay, so 5 times the square root of 5 is 5 times 5. I'll just simplify that to 25. The two middle terms are like radicals, so those can be combined by subtracting. So we get a total of plus 19 times the square root of 15. And the square root of 9 is 3, and minus 4 times 3 is minus 12. So the last step is 13 plus 19 times the square root of 15. Okay, we'll look at a few examples where we rationalize denominators. Okay, we'll do 3 or 4 of these and then go on to the next topic. If there's time left at the end, I'll come back to some of the ones we didn't do. Okay, this one, 5 divided by 3 plus the square root of 7. Well, there's an irrational number. The square root of 7 is in the denominator. So we want to rationalize the denominator. In the end, we want a number that's equal to this number, but with no square root in the denominator. So we multiply by 1, and the form that 1 takes depends upon the denominator that we start with. 3 plus the square root of 7, well, the conjugate of that is 3 minus the square root of 7. So we're going to multiply by 1 in the form 3 minus the square root of 7 over 3 minus the square root of 7. So in the numerator, multiply 5 times that quantity. We get 5 times 3 is 15, and then minus 5 times the square root of 7. And in the denominator, 3 times 3 is 9, and then minus 3 times the square root of 7, then plus 3 times the square root of 7, and then minus the square root of 49. So the numerator for now is just 15 minus 5 times the square root of 7. In the denominator, the two middle terms cancel each other out. Those add up to 0. The square root of 49 simplifies to 7. So we just get 9 minus 7. And then there's one more step. 9 minus 7 in the denominator is 2. And then the numerator, 15 minus 5 times the square root of 7. This number has exactly the same value as the original number, but it no longer has an irrational number in the denominator. So we succeeded in rationalizing the denominator. Okay, the next one is, I'll just tell you what to multiply by 1, or what form 1 should take, and then I'll leave the rest of that for you to do. The denominator is the square root of x minus the square root of 5. So in order to rationalize the denominator, we multiply by 1 in the form the square root of x plus the square root of 5 divided by the square root of x plus the square root of 5. Okay, so multiply all of that out and simplify, and in the end, there will be no more square roots in the denominator. Okay, the next example, 5 divided by the fourth root of 3. Well, the denominator is irrational because of the radical, the index 4. So we want to multiply by 1. And first, note that the fourth root of 3, what we want is the fourth root of a perfect fourth power. So we ask, what would I have to multiply by 3 to the first to get a perfect fourth power? The answer is 3 to the first times 3 to the third is equal to 3 to the fourth. 3 to the fourth, by definition, is a perfect fourth power. So the form that one takes is the fourth root of 3 to the third divided by the fourth root of 3 to the third. 3 to the third is 27, so we do want to write the numerator as 5 times the fourth root of 27. And then in the denominator, the fourth root of 3 times the fourth root of 3 to the third is the fourth root of 3 to the fourth. 3 to the fourth is 81. 81 is a perfect fourth power. So our final answer is 5 times the fourth root of 27 divided by 3, because the fourth root of 81 simplifies to 3. So now we have rationalized the denominator. Okay, this one is a similar type of process. This time it's 9 divided by the cubed root of 49y. Notice that 49 is 7 to the second. So the number that we would have to multiply by 7 to the second to get a perfect third power is just 7. 7 to the second times 7 is 7 to the third, which is a perfect cube. And then the factor y, or y to the first. I would have to multiply y times y to the second to get y to the third. Okay, so the form that one takes on this one is the cubed root of 7y to the second divided by the cubed root of 7y to the second. So in the numerator, we have 9 times the cubed root of 7y to the second. In the denominator, the cubed root of 49y times the cubed root of 7y to the second. Well, that's the cubed root of 7 to the third, or 343. 343 is just a perfect cube. 7 to the third is 343. And then y times y to the second is y to the third. And then in the last step, we can write the numerator 9 times the cubed root of 7y to the second. And in the denominator, the cubed root of 343 is 7. And the cubed root of y to the third is just y, which is y to the first. Okay, the final example here, the square root of 5mn divided by the square root of 125m n to the 8th. Well, with practice, you can notice some things that will make things easier. And you don't need to, it's not really required to write it as a single square root, but it might be helpful to see what's going on. The quotient 5mn over 125m n to the 8th, or sorry, n to the 9th, can be written in lower terms. So we get the square root of 1 over 5n to the 8th. Because 5 over 125 is 1/5. The m's cancel, and n over n to the 9th simplifies to n to 1 over n to the 8th. And then the square root of 1 in the numerator is 1. And in the denominator, sorry, I wrote 5. This should be 25. 5 over 125 reduces to 1 over 25. And then the square root of 25 is 5 in the denominator. And the square root of n to the 8th is n to the 4th. Okay, I think we'll be able to cover everything that we want to cover today. From section 8.6, we'll solve some equations with radical expression. So on this one, we have the square root of 5x minus 7 equals 7. At this point, it doesn't not make sense because the left-hand side is the positive square root and the right-hand side is a positive number. So no red flags yet. We want to solve for x. X is inside a square root. So to get it out of the square root, we square both sides. So square the left-hand side, square the square root of 5x minus 7, and on the right-hand side, square 7. When you square the square root of 5x minus 7, you're just left with 5x minus 7, and when you square 7, you get 49. And then add 7 to both sides. 5x equals 56. Then divide both sides by 5. X equals 56 divided by 5. And you can check and verify that this is the solution. It's only a couple of steps to check it. And it turns out that it works out. Okay, the next one is a little more involved. Solve this equation. The square root of 3x minus 2 equals x minus 2. X appears in more than one place, but since it does appear inside a square root, that means we want to square both sides so that we can get it out of the square root. So we're going to square the square root of 3x minus 2 on the left-hand side, which means we have to square the binomial x minus 2 on the right-hand side. When we square the square root of 3x minus 2, we just get 3x minus 2. And when we square the binomial x minus 2, we get x squared minus 4x plus 4. Then we just have a quadratic equation, so we'll get it into standard form. We'll subtract 3x from both sides and add 2. So we get 0 equals x squared minus 7x plus 6. This factors nicely. We can solve by factoring. One factor is x minus 1. The other one is x minus 6. This quadratic equation has two solutions. One is x equals 1 and the other one is x equals 6. Okay, when we check these, you can tell almost right away that x equals 1 is not going to work. So when we test x equals 1, replace every x with 1, we get on the left-hand side the square root of 3 times 1 minus 2. On the right-hand side, 1 minus 2. So on the left-hand side, we get the positive square root of 1, because 3 times 1 minus 2 is 1. On the right-hand side, we get negative 1. And that is false, because the left-hand side is positive 1. So 1 is not a solution. 6, however, is a solution. You can pretty much tell by looking, but if you replace x with 6, we get the square root of 3 times 6 minus 2 equals 6 minus 2. 3 times 6 is 18. 18 minus 2 is 16. And so the positive square root of 16 equals 4. That's true. So x equals 6 is the only solution. Okay, a couple more. This one is the fourth root of 5r plus 3 equals 3. Since the index is 4 and the variable we want to solve for is inside the radical, we want to raise both sides to the 4th power to get the variable out of the radical. So raise both sides to the 4th. When you raise the 4th root of 5r plus 3 to the 4th, you just get 5r plus 3. And when you raise 3 to the 4th, you get 81. And so we can easily solve for r. 5r equals 78. Divide both sides by 5, r equals 78 fifths. And it's not hard to verify that this really is the solution. Just replace r with 78 fifths, do the arithmetic. You'll end up with the 4th root of 81 after doing the arithmetic, so it works out pretty nicely. Okay, this next one, solve 5 times the square root of x equals x plus 6. Okay, here's a case where my suggestion is, instead of dividing both sides by 5 first, just square both sides in the first step. That's my suggestion. You don't have to. You would just undo what you did if you do divide by 5 on both sides. Okay, so remember what it means to square something. When you square 5 times the square root of x, it means 5 times the square root of x times 5 times the square root of x. And that is 25x. And x plus 6 quantity squared is x plus 6 times x plus 6, which is x squared plus 12x plus 36. And we get a quadratic equation, so subtract 25x from both sides, and we get 0 equals x squared minus 13x plus 36. And we can solve by factoring. This factors really nicely. One factor is x minus 9, and the other one is x minus 4. And you can always check by multiplying that your factoring is correct. The two solutions to the quadratic equation are x equals 9 and x equals 4. I'll leave the rest for you to do, which is to check. I'll just point out, though, it's pretty easy to check. Replace every x with 9. 5 times the square root of 9 is 5 times 3, or 15. And on the right-hand side, 9 plus 6 is 15. Well, I guess I'm checking, aren't I? So x equals 9 is a solution. Then when you replace x with 4, 5 times the square root of 4 is 5 times 2, or 10. And the right-hand side, 4 plus 6 is also 10. So both numbers are solutions in that case. Okay, we'll look at the last section that you're going to be tested over on Friday, section 8.8 on square roots of negatives. Okay, so this is not too hard, but behind the square root of a negative number is this definition. The square root of -1 is called the imaginary unit, and instead of writing the square root of -1, we just write I in its place. Okay, so the square root of -49, think of that as the square root of 49 times the square root of -1. Because the product property of radicals says we can do this, we can write a product of radicals. So the square root of 49 is 7, and then we replace the square root of -1 with I. So the answer is 7 times I, or just 7i. The square root of -81, same idea. Using the product property of radicals, this is the square root of +1 times the square root of -1. Replace the square root of 81 with 9, and replace the square root of -1 with I. So 9 times I is what it simplifies to. Okay, so you should expect some more involved situations. So to simplify the square root of negative 175, the largest factor of 175 that's a perfect square is 25. So we'll think of this as the square root of 25 times the square root of 7 times the square root of negative 1. And if you multiply those, you'll get negative 175. Okay, so the square root of 25 is 5 multiplied by the square root of 7, and then replace the square root of negative 1 with I. This is our simplified result. Okay, the next one, the square root of negative 128. Well, 64 is a perfect square, and 64 times negative 2 is negative 128. I'll write a little bit more detail on this one. Think of the square root of negative 128 as the square root of 64 times the square root of negative 2. We'll go ahead and simplify the square root of 64 to 8, but then write the square root of negative 2 as the square root of 2 times the square root of negative 1. And then finally, 8 times the square root of 2 times I is our simplified answer. It's not necessary to go into all that detail, but you can if you have to. Okay, on the next one, let's write this as the square root of negative 160. We know that 16 is a perfect square, and 16 times negative 10 is negative 160. So we can write this as the square root of 16 times the square root of 10 times the square root of negative 1. And our final answer is 4 times the square root of 10 times I. Here, the last one on this page, the square root of negative 63. 9 is a perfect square, and 9 times negative 7 is negative 63. So write this as the square root of 9 times the square root of 7 times the square root of negative 1. And then the square root of 9 is 3. We have to multiply 3 times the square root of 7, and then replace the square root of negative 1 with I. Okay, so we saw a sample of the problems that will be on Friday's test. So I do have more than a minute left, so I could do this problem that we skipped over earlier. We're adding and subtracting some radicals. So we might be able to get through this. The fourth root of 48r to the 10th. The largest factor of 48, that's a perfect fourth power, is 16, because 2 to the 4th is 16. The largest factor of r to the 10th, that's a perfect fourth power, is r to the 8th, because 8, the exponent 8 is a multiple of 4. So you can rewrite this as the fourth root of 16 r to the 8th multiplied by the fourth root of 3r to the 2nd. Okay, then the largest factor of 243, that's a perfect fourth power, is 81. So you can rewrite the next term as the fourth root of 81 r to the 8th times the fourth root of 3r to the 2nd. And then in the next radical, the numerical factor can't be simplified further, but the largest factor of r to the 10th, that's a perfect fourth power, is r to the 8th. So this is the fourth root of r to the 8th times the fourth root of 3r to the 2nd. Okay, so we're out of time, but simplify the fourth roots of the perfect fourth powers, and they are all like terms that can be combined by adding and subtracting. Okay, so that's all for today. And so make sure that you can sign into Zoom so that you can take the test 3 on Friday.